Hi, I'm Andrei Bielikov, and today I will show you one of my projects, the so-called sapling compiler. So the sapling compiler is a compiler that, instead of compiling a single language and generating machine code for it, it compiles multiple languages defined in a file and also on top of each other. In a way, one could say that it compiles horizontally, in the sense that in a single source file there can be multiple languages written, and it also compiles vertically because you can stack those languages in a way that one language translates to the other and that one translates to another, and in the end what you get is a file with the output of all translations, both those defined in one language and also the fragments of code that have been written in the highest language of a stack translated to the lowest. So let's show you how it works. Here it complains that there is no input file. Let's see the help for it. Okay, so here are the synopses. Sapling accepts an input file, and optionally with the O option you can specify an output file where you want to write it. Usually this is an a.out file by default. Then we got another synopsis with the M option. This is the so-called meta mode. The meta mode makes reference to the meta grammar, or as I call them, specs, which are language specifications. So unlike other tools, for example, Flex, Bison, and whatever hosting language you might use with those tools, where you have to specify the terminal separately, the productions and non-terminals also separately, and you also have to, using the productions, specify the semantic routines in a host language, like for example C or Java or whatever. So Sapling is different from all those tools in the sense that it is an integrated solution. So here you can see in a single file there are tokens and also the productions. Now I mentioned that in other tools you have to specify the semantic routines in the host language, and it's a really smart choice because those languages are powerful enough for the synthesis of the output. But I went for a more integrated approach. Now this grammar or spec does not have any semantic routines. That is because Sapling has a built-in Lisp-like language for the semantic routines, but it's not powerful enough to recreate the sapling compiler itself. So what I use this specification for is to get the Lexer automaton and also the SLR parsing tables, and then I use a set of shell scripts which are written in bash in order to regenerate much of the compiler's code in a process called bootstrapping. So Sapling has three built-in languages. One is the meta language, which is the analysis language, which is the language with which you specify the specifications or grammars in the broader sense. There is also a composition language, and this language is what allows us to define fragments of code and the language in which they are written and the language to which they must be translated, as well as fragments which are written in the highest language of a language stack. And finally, there is the language, the built-in language for the semantic routines, which is a form of Lisp, which but is actually a subset. It does not work exactly, and it's very small still and not very powerful, but I will show you some examples. And I've called it micro Lisp. So many of these folders have code that is generated from the Lexer automaton generated from the terminals, and it also has an automaton that is generated from the productions. So the scripts they regenerate things such as the terminals, the definition of the terminals, the definition of the non-terminals. There are also productions, and the important thing, this is the Lexer of the composition language. It's just all C code. The routines that depend on the information that depends on the grammar specification that is generated from it. And there is also the parser. Oh well, the parser has various levels of actions that do different things based on how far they are from the basic needs in order to parse the language, in order to successfully parse it and accept it. And here is the automaton. This is generated from the goto table, while this function over here is generated from the action table. And what you can also generate is a file of a level that I call to, which is the actions that you can do on a production reduction, on a reduce. And so you can get you can also navigate the tree of each of the nodes of the production symbols and extract information from them. Now this one is small. This is the composition language, but others like the meta language have a very big code for the action files, for the actions on reductions. So let me show you an example of a specification that has list routines. For example, this one, actually not this one, this one is a translator that translates 6502 assembly to binary. Here you can see that this production has an associated semantic routine that emits the byte. These are immediate mode instructions, so they only need one byte with no parameter, so they only emit one byte. For disabling the interrupts, it's 0x78 hexadecimal, and for clear decimal mode is 0xd8. Another example is a language that translates from hexadecimal written literally to binary, and what the semantic routine does is it extracts the lexeme, which is, let me show you, is the literal text parts of every hexadecimal entry. It passes them to a mapping of the C function str string to long from the C standard library, and this returns an integer which then is emitted as a byte to the output. So in this file we can see that there are a few fragments. The first one is written in the hex2bin language, and this one specifies the so-called INS header. And here we have a fragment in 6502 assembly code, which translates C and CLD to binary. Now let's see what we can do. For example, is use sapling. So we specify this input file, which is from the build directory in test 6502 input file, and we will output it in sapling test 6502 output file, or let's just call it game.nes because it is the final binary. Okay, so here there is some debug information, but at the beginning what it does is it has a cache of compilers, and it creates from each file that it finds a compiler, a runtime compiler, and it does it once for each unique file that it finds this is a specification, a composition file, because it's made out of fragments. And so it compiles the compiler, and then it runs that compiler with the input that is inside of the fragment code. And it also does it with the second one. The debug information that you see here is the stack of microlisp. And this stack is useful to see if, for example, ifs work correctly, because this, even though it's not powerful enough, this microlisp is so the routines. These routines are compiled into microlisp parse trees, which then are executed from the bottom up. And in order to avoid the execution of the lowest parts of the tree, actually let me show you. So let's use the meta mode on the spec sample 6502 to bin, and let's specify the option to print the micro Lisp parse trees. Actually, it's called dump. If it's a graph specified in dot language, is usually dump. So these productions do not have an associated semantic routine, but this does, and we will visualize how it looks. So here's the parse tree for that micro Lisp routine. And so what happens is it first goes to the bottommost parts, and it evaluates each leaf and propagates the value up, and it puts it on a stack. The problem is, for example, init byte does not return any evaluation. What it does instead is print out the output to the output file, but we don't want to do it at the bottom because it still has not evaluated the if. So what we do instead, as first when we go down, if we find an if, we increase the number of nested ifs, and if any function wants to execute inside, then it cannot do so. Instead, it is converted into a function atom, and every function knows the number of parameters it accepts, and instead of being executed, it is saved on a stack. And later, when we exit all ifs, for example, the conditions are this. Now this argument here is the condition, which is then evaluated at the highermost if. And if it is true, then this part is executed, and this branch of the tree is pruned from the execution. Or otherwise, if the condition was false, this branch is pruned from the execution. We follow this one. We now evaluate the if. We run the functions that are lower on the tree that could not run before, and the same thing. So here's the condition, this argument here, and if it's true, this gets executed and this pruned, and otherwise this gets pruned and this gets executed. So it's a bit like lazy evaluation. Okay, and so this has outputted a file, but let's see what is inside there. So let's run hexedit test 6502 output file. No, it's game.nes. So here we can see it in hexadecimal with the hex editor. So these are the same values that we specified here, and say and CLD are the first two instructions that are codified as the last two bytes. And here we can see that say and CLD are also 078 hexadecimal and D8 hexadecimal. This example, however, does not have an example of stacked languages. So let's see a simple example of a specification file with a composition file or a composite source with multiple fragments and with language tags. This is called the vegetables example. So what it will do, this fragment, it will first, this is the hightmost language, and this is the language in which the fragment is written, and so this will first translate this language it will translate this from English to Castilian according to the rules of the first spec. Then the output of this translated with this will feed into this, and then the same will happen for this, and in the end what we will have is an output that was in English, that was then translated to Castilian, then to Catalan, and then to Polish. And here we have another fragment which we have used the hex-to-bin language specification, and this will also output in the output file. This is a new line. These are new lines, and this is the string hello in between. So let's run it. Let's see, test vegetables input file output. We want to output in test vegetables output file, and here we can see that it has translated this to Polish finally, and this has been translated to hello. We can try to comment out the final language and see what we get. So here we left the Catalan to Polish, so it stays in Catalan. It stops at Catalan, and then if we remove the Catalan, it stays in Castilian. And well, we don't want to remove the only language, because otherwise the compiler will not know what to do with it. Another interesting thing about sapling is the diagnostics options. So you can do things like print the lecture output only, log the state stack and the nodes of the stack of the nodes of the parse tree during parsing. This option does not invoke the parsing. This only invokes the lecture, and it simply prints all the terminals that have been identified in a file. This dumps the parse tree of the input file, and then well, this is only for specification files. And then for a specification file, it can also print the terminals from the specification, the non-terminals, the productions. It can also print the lecture output. This is used to especially to regenerate the code for the built-in languages, the composition, meta, and microlisp languages. It can dump the lecture automaton in the dot language. It can print the SLR tables in a formatted manner, and as we see, we used it before, it can dump the microlisp routines into a parse tree, and that parse tree is executed as is from bottom to up, with the treating ifs specially to defer evaluation to later. Okay, for example, let's see an example of the meta grammar. Sapling meta mode spec meta. Okay, so if you do not specify any extra options, it simply tells you if this is a correct, in this case it is the meta spec. It simply tells you if this text is accepted by the language grammar, by the grammar that specifies a grammar. If we choose print lecture output only, it prints all of these. These are the integer IDs, these are the strings, and these are the lexemes of the terminals. We can also, for the parser, log state stack, and we can also log the parse tree stack, and this shows us the evolution of the stack, of the parsing and the stack for building the parse tree. What else? So another thing we can do is we can dump the parse tree, dump parse of the, by the way, all graphs are outputted as a single line with no spaces in between, so you can just copy this is only one line, Ctrl A, Ctrl V, and you have the parse tree of the metagrammar file with according to the metagrammar. Yes. So let's see what else. We can print the terminals of this grammar. We can print the non-terminals. We can also print the productions. We can print the lecture automaton that classifies lexemes to a particular terminal class. By the way, global classes mean that they do not pass to the parsing stage. These terminals are not emitted to the parsing stage, so you can use it for things like comments and removing blanks. Now, if we dump the lecture automaton, here, as you can see, this junction is simply a pipe character. The symbol are lowercase characters from A to Z, and then starting from the second character we accept 0 through 9, and also the underscore. Then we also accept classes. The dot means it accepts any character. The dot with the dashed edge, and the final states hold the class information which you can extract. Let's see what else we have. So very interesting, the SLR tables. So here you can see the SLR table for the metagrammar, formatted beautifully. This is processed to generate the code for the SLR automaton in C code. And the other thing, the final function which we had already seen, is for dumping the microlisp parse trees for the microlisp routines for each production. And this is pretty much all that sapling does. Thank you.